In theory, we already have all of the knowledge that we need to answer questions in probability theory. In practice, what we'll find is that many situations which at first look to be completely different situations, you might be talking about cereal in one instance, and in another instance you might be talking about engines. So you think they have nothing in common, but in practice they have a lot in common. It makes sense to study these situations in more general terms, to find out what it is that they do have in common, to prove results or to state results. In this course, we're not proving anything, that apply to all of these apparently completely distinct situations to solve the problems of interest. We'll start by doing so for discrete distributions, discrete situations. A random variable is a function of a sample space. You'll remember that is the set of all possible outcomes of some random experiment into the set of real numbers. So it's a rule that associates a real number to an outcome of a random experiment. S is the domain, and if you apply a random variable x to the domain, you get its range. A probability distribution function, a PDF, also sometimes called a probability density function. It's a function which specifies the probabilities of the values in the range of the sample space. When your sample space is discrete, heads or tails, potentially roll the die, you get 1, 2, 3, 4, 5, 6. We say that the random variable is discrete, the function is discrete, and the PDF in that case is called a probability mass function, a PMF. We're going to use the same notation throughout here to make things easier to follow. Capital Roman letters, X, Y, Z, and so forth, these will denote random variables. And when we use the corresponding lowercase Roman letter, little x, little y, little z, we are denoting a generic value that can be taken by the random variable. Now you can use discrete random variables to define events. Say that your random variable takes on the values xi, so potentially x1, x2, x3 all the way up to xn. Then your events A1, A2, A3 all the way up to AN would be the set of all outcomes in the sample space for which, when you apply the function to that outcome, you get xi. In that case, the probability mass function of the random variable x is going to be a function f, and it's the probability of that specific event. The probability that the random variable big X is equal to little x. In this instance here, x is meant to be general. It could be anything, but then you can imagine asking for the value of f1, which would mean you're asking for the probability that your random variable x takes on the value 1. The cumulative distribution function is a function which is associated with the PDF or the PMF, as the case may be. Here you are looking for the function which corresponds to the probability that the random variable would be smaller than or equal to little x. What are their properties? Well, if you have a random variable x which is discrete, and let's say that it has a probability mass function little f and a CDF big F, then these are the things you know. The value of the function f, the PMF, at any x in the range of the random variable has to reside between 0 and 1. In theory, it could also be 0. The inequality here does not have to be strict, but for outcomes where the PMF takes on the value 0, what you're saying is that there is no probability of that outcome happening. So if there's no probability of the outcome happening, it can't happen, so it's not really part of the sample space to start with. Right? It's not one of the possible outcomes. So we will denote it using the strict inequality. The other thing that we know is that if you look at all the possible outcomes and you compute the value of the PMF at each of these outcomes and you add them up, it has to add up to 1. The probability that one of the outcomes will occur when you run the experiment is 1, right? Because if you run the experiment and you get an outcome which isn't one of your possible outcomes, what this really means is you hadn't identified the right set of outcomes to start with. So whenever you run the experiment, something must happen, and that something must be one of the possible outcomes. This is what this is saying here. If you have an event A, which is to say a set of possible outcomes, the probability that X is an A would be equal to the sum of all of the values of the PMF for all X's in the event A. So for all the possible outcomes in the event A. The probability that A would be strictly smaller than X, that's going to be the same thing by the rules of probability as the probability that A is not strictly smaller than X, and you subtract that value from 1, right? So this thing here would be equal to 1 minus this. Or another way to write it, if A is not strictly smaller than X, it means that X must be smaller than or equal to A. And this, we have an expression for it. That's the value of the cumulative distribution function at A. So you can compute expressions of this form. Yeah, so what about expressions of this form? This you already have. That is f at A. That's good. And you can also compute expressions that look like this. What's the probability that the random variable takes on a value strictly smaller than a number? That's not the same thing as smaller than or equal. Well, if you're working with discrete distributions, that would be the probability that your random variable is smaller than or equal to b, the same upper bound, minus the probability that it is equal to b. In other terms, big F of b minus little f of b. The only other thing you might be interested in computing, probability-wise, would be the probability that A is smaller than or equal to X. Again, that is not the same thing as what you've already found before, right? We found the probability that A would be strictly smaller than X. That's not in general going to be the same as the probability that A is smaller than or equal to X. By the rules of probability, the probability that A will be smaller than or equal to X is going to be 1 minus the probability that that's not the case. And it's not the case when X is smaller than A strictly. That's the probability that you want. This expression, we have an equation for it on the previous slide, except we used B instead of A. That is this expression here. Big F at B minus little f at B. So we have 1 minus this expression, 1 minus big F at A plus little f at A, once we distribute the minus sign to these things. So all of these results can be used to compute the probability that a discrete random variable will fall in various intervals. So there's 4 different intervals: a strictly smaller than x less than or equal to b, a less than or equal to x less than or equal to b, a strictly smaller than x strictly smaller than b, and a less than or equal to x strictly smaller than b. And you compute all of the probabilities here using either the values of the cumulative distribution function at various points, or the values of the probability mass function at various points. Alright, now if you're anything like me, you just saw that first 2-3 slides and you're like, what is going on here? Let's do a few examples that will explain what actually is going on. Imagine a situation where you're flipping a fair coin. Perhaps the outcomes are heads and tails, as we've seen. We will build a random variable x, and this is how x is going to assign numbers to the outcomes. If you flip head, the number that is assigned is 1. If you flip tail, the number that is assigned is 0. So it is a discrete random variable, and we will write typically x equals 1 and x equals 0 to mean I flipped the head or I flipped the tail, respectively. Now, if your coin is fair, you are just as likely to flip heads as you are to flip tails, and so the probability mass function, which computes the probability that you would flip tail or heads, should take on the constant value 1/2. What this is saying here is that you have a 50% chance of flipping a tail, x equals 0, a 50% chance of flipping heads, x equals 1, and a 0% chance of flipping any other result. So what's the value of f at 1/2? Well, that's 0, because the only thing that you can put in here to not get 0 is either 0 or 1, and 1/2 is not 0 or 1. We can verify that the properties of PMF apply. Yep, the values of possible outcomes are found between 0 and 1. 1/2, 1/2, that's between 0 and 1. You'll say, well, what about this one? Sometimes the value of a function is 0. Yes, but these are the outcomes that are not possible. Right? The value of f has to be between 0 and 1, strictly larger than 0, only for the possible outcomes. And if you add up all the probabilities, they do sure enough add up to 1. Now imagine that you roll a fair die. The outcome space, we have 1, 2, 3, 4, 5, 6. Each one of these results is equally likely. We define a random variable which is going to be, well, the actual number of dots that you roll on your die. So if you roll your die and you get a 3, the value of the random variable that corresponds to that roll is 3. If the die is fair, the probability mass function is going to be exactly 1/6 for the values 1, 2, 3, 4, 5, 6, and it's going to be 0 for everything else. What's the probability that you roll the value pi? 0. There's a 0% chance of that happening. What's the probability of rolling the value 4? It's going to be 1/6. Again, the properties are satisfied. All of the PMF values that correspond to possible outcomes are strictly larger than 0 and smaller than or equal to 1, because 1/6 is between 0 and 1. And if you add up all of its possible values, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, you get exactly 1. One of the things that is not obvious to do at times is how to build the CDF from the random variable, from the probability mass function. This function here, the CDF, is not obviously given to you. This is one of the ways in which you can write it. What's the probability that you will roll a number smaller than or equal to x? Well, it depends. What's the probability that you're going to roll a number smaller than or equal to 1/2? Well, that's 0. It is impossible for you to roll something smaller than 1/2, because you can roll a 1, a 2, a 3, a 4, a 5, or a 6, and all of these numbers are larger than 1/2. What's the probability that you'll roll a value which is smaller than 3/4? Again, that's 0. Now, what's the probability that you would roll a value smaller than or equal to 1? Here there's a possibility, right? You might roll a 1. That's the only one of the 6 values that meet this criterion. So you would expect that the probability of rolling the die and getting less than or equal to 1 dot, that should be 1/6. But what about the probability of rolling something which is smaller than 1.1, say? Well, that should be the same probability, right? In order to roll something smaller than 1.1, the only way you could do this is by rolling a 1. And that's the same thing as the probability of rolling something smaller than or equal to 1, which is 1/6. So I'm going to give you a chance to try to graph or chart what this probability function looks like when you chart its cumulative distribution function. When you're working with discrete variables, you can also, instead of using the formulas that I've given you to compute the probability of the random variable falling in an interval, you can compute it directly. It might take a while to do so, but it's at least something that is conceivable for you to do. For this specific random variable, what's the probability that you will roll something between a 3 and a 5 inclusively? Well, that's going to be the probability of rolling a 3 plus the probability of rolling a 4 plus the probability of rolling a 5. Each of these probabilities is 1/6. There are 3 of them, 3/6 or 1/2. But you could also use the formula that I've given you. The probability of rolling something between 3 and 5 inclusively would be the cumulative distribution function at 5 minus the cumulative distribution function at 3 plus the probability mass function at 3. And if you work it out, 5/6 minus 3/6 plus 1/6, you're using here this description of the cumulative distribution function and this description of the probability mass function, you will get 1/2. The number of calls you might receive over a specific time period, if you call that x, that's also a discrete random variable. Like in the next hour, I might receive 0 calls, 1 call, 2 calls, 3 calls, and so forth. Now, without knowing more information about the problem, I can't really compute probabilities here. Let's say you have a 5-card poker hand. So you've picked 5 cards from a deck of 52 cards, where you had 13 cards of each suit: diamonds, hearts, clubs, and spades. So what's the probability of the random variable x, where that indicates the number of red cards in the hand? If you pick 5 cards, or if you draw 5 cards, or if you're dealt 5 cards, you cannot have more than 5 red cards in your hand. But you can't have less than 0 red cards in your hand. The only values that x can take will be 0, 1, 2, 3, 4, or 5. Now we know from what we saw in the first chapter that you have 52 choose 5 ways to select 5 cards from a 52 card deck. If you want, that's 52 factorial divided by 5 factorial divided by 52 minus 5 factorial, right? In other words, if you're picking 5 cards, you have 52 choices. For the first one, it'll be 51 choices. For the next one, 50 choices, 49, 48, right? And that's going to be the same thing as 52 factorial divided by 52 minus 5 factorial. But on top of that, you don't care about the order in which these cards are given to you. Right? So this could be the first card, the second card, the third card, fourth card, the fifth card, or some other combination of these things, and you obtain that by dividing by all the possible permutations of these 5 slots, these 5 positions. So that's exactly 52. Choose 5. So these are the values that your random variable can take: 0, 1, 2, 3, 4, 5, the number of red cards. If x equals 0, that means that you have no red cards. Every card that you have is black, either a spades or a clubs. So we'll look at the number of red cards you have picked from there. Well, you've picked 0 from a set of 26. 6 choose 0. And every single one of your cards will be black. 26 choose 5. So in total you have 26 choose 0 times 26 choose 5 number of hands that only contain black cards divided by the total number of cards that you have, 52 choose 5. We won't care about what the value of that is for now. We'll just say this is how you would compute it. The number of 5 card hands that only contain black cards divided by the total number of 5 card hands. Now, if you pick some other value of x, anything between 0, 1, 2, 3, 4, and 5, you're going to have 26 choose x ways of having exactly x red cards in your hand, and 26 choose 5 minus x ways of having 5 minus x black cards in your hand. Because if you have 2 cards that are red in your hands, well, there's 26 2 ways of doing this, and that means that you will have then the other cards that are not the 2 red cards have to be black. If 2 of them are red, 3 of them have to be black, so there's, you pick 3 from the set of 26 cards. Well, the general formula then would be 26x, 26, 5 minus x. So in general, the probability of having exactly x red cards would be given by this expression. We won't be talking about this distribution in general terms, but it has a name. This is the hypergeometric distribution. So in your textbook, you could learn a little bit more about it. The values that x can take would be 0, 1, 2, 3, 4, 5. If this is indeed a probability mass function, each of the values, f0, f1, all the way up to f5, have to fall between 0 and 1, and the sum of the values has to be equal to 1. That's the only option. You gotta have 0 red cards, 1, 2, 3, 4, or 5 red cards. There's no other possibilities. Here's another example. How would we find the cumulative distribution function of a discrete random variable x if we know that the probability mass function is going to be 0.1x if x is equal to 1, 2, 3, 4, and 0 otherwise? This is what this probability mass function would look like. 0% chance of having a 0 or anything before 1, and then a 0.1 chance or 10% chance of getting a 1. Then you'd have a 20% chance of getting a 2, 30% chance of getting a 3, and 40% chance of getting a 4. Everything else is 0. Sure enough, 10% plus 20% plus 30% plus 40% adds up to 1. That's what we're seeing here. We're adding up all of the possible values that this probability mass function can take. So that's 0.1x, that's given, where x can go from 1 to 4, and everything else is 0, so it's not in there. And then we use the rules that we have for these summations. That gives us 0.1 times the sum 1 plus 2 plus 3 plus 4. You can compute it directly, or you can use some of the formulas you might remember from high school. Sure enough, you get 1. Then the cumulative distribution function would take on this value. There's 0% chance you will obtain something which is strictly smaller than 1, because the probability of getting something smaller than 1 here is 0. Then there's a 10% chance you will pick something which is either 1 or strictly smaller than 2, on account of, well, you have a 10% chance of getting a 1 and 0% chance of getting anything else between 1 and 2, and so forth and so forth and so forth for all of them. So this would be your cumulative distribution function. How do we read this? Really what this is saying is that if you want to know what the probability is of picking something which is, say, smaller than 2.7, you would find the location on the graph which crosses the vertical line 2.7, and then you find the equivalent height to be here at 0.3. So you have a 30% chance of the random variable taking on a value smaller than 2.7. What are the values that it can take that are smaller than 2.7? It can take on the value 1 or the value 2. The value 1 accounts for 10% and the value 2 accounts for 20%. And when you add those together, 10 plus 20, you get your 30% right here.